Welcome to Alchem, helping you understand chemistry one step at a time. There are many functional groups that contains carbonyl group. First, I want you to find one or two common things that you see in these structures. Yes, you've got it. They've all got R groups, but more importantly, they all have C2O double bonds. The word carbonyl or carbonyl group means C2 double bond in the organic structures. The two carbonyl groups that I'm going to master today are aldehydes and ketones. I share this with you because I've seen too many students losing mark unnecessarily. As a national and international marker, I want to show how examiners actually think. Here are first tips. When you face question to identify or circle the functional groups, you must include carbon, oxygen, and hydrogen for the aldehyde. For ketones, it is really important to include both neighboring carbons. Otherwise, if you circle only C2O double bond, it can be also found in carboxylic acid, acid chloride, ester, and amides. So remember this and let's get it started. Here are some general information about aldehydes. It is always found at the end of the chain, and the R group means rest of the molecule. It can be hydrogen or single carbon or much more complicated structures that is just attached to it. And the suffix anal might come quite handy because if you read it as anal, the rear end, so you know it's always going to be at the end of the chain. General formula, it has double amount of hydrogen compared to a carbon with one oxygen. In condensed formula, it ends with CHO, and aldehydes are usually produced from the oxidation of primary alcohol, which we're going to look at in a different video. Let's get into the business. So I'm bringing up 6 carbons in a row and aldehyde at the end of the chain, and let's see if it matches the general formula. Having 6 carbons, we should expect to have 12 hydrogens. We already have 1 hydrogen shown, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the general formula is written as C6H12 oxygen. And we got 6 carbons, which is the maximum number of carbons in this case, which contains the functional group of aldehyde, so starting with a prefix hex to represent 6. Then we've got an aldehyde, so we just got to put the suffix as anal, remember? But we don't read this as a hexanal, it's hexanal. And because aldehyde is always at the end of the chain, there's no need to number the name. So it's just a hexanal. And let's try condensed formula, reading from left to right. So we have CH3, CH2, 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 and finishing with CHO to represent the aldehyde. But since we have 4 repeating CH2 groups, we can even condense this further by using brackets CH3, CH2 brackets 4, then CHO. What you need to be careful is not to write this as a COH for the aldehyde group because it may represent the alcohol instead of the aldehydes. So let's try the skeletal formula. Remember, I've seen so many students drawing extra lines or one less line. So here's your exam tips. Having 6 carbons, try using pencil and dot 6 carbons like so. And just connect them over the dots, so that gives you 6 carbons in a row. Then all you gotta do is put double bond with oxygen and single bond with hydrogen. You can make the last dash a little shorter so you have a space to write hydrogen. Let's bring a slight variation. Still dealing with 6 carbons, but this time we'll have 5 carbon in the main chain, aldehyde at the end, and bring the last carbon as a side chain. And it'll still have 12 hydrogens altogether with the same molecular formula to the previous one. So it's an isomer to the first structure. So identifying the longest chain that contains the functional group, which has 5 carbons, so the prefix, we're going to start with pent. And having this aldehyde, we will have the suffix anal. So it's a pentanal for the main chain. But this one is important to be numbered to show the location of the side chain. So start numbering the carbon of the aldehyde, keep continuing, and there's a methyl group coming off the fourth carbon. So the name goes 4-methyl pentanal. And the condensed formula reading from left to right, it is CH3CH, but remember that methyl group highlighted in yellow is the side chain, so must be in brackets too. And if you actually want to advance a little bit, trying to see the structure from this point of view where you see two methyl groups hanging off. So you can start by putting CH3 brackets 2, followed by CH, which is the fourth carbon, then CH2, CH2, finishing with CHO. So same with skeletal formula. Since this one has only 5 carbons, you can do 1, 2, 3, 4, 5. And the direction, whether you go up first or down first, it doesn't really matter. So we've got 5 aldehyde doubly bonded O with hydrogen, and just come back to the fourth carbon and add the methyl group. Remember, skeletal formula, you don't have to show the carbon, so that's it. Just going to show you one more structure that can deal with 6 carbons altogether, but we've got 4 carbons in the main chain of aldehydes, but 2 extra carbons are coming off as a side chain. So it adds up to 6 carbons with 12 hydrogens altogether when you add up. And this time we have 4 carbons, so we are starting with a prefix bute. All right, remember this is not but, it's a bute having aldehyde, butanal. And numbering the main chain starting from the aldehyde, and the methyl group is coming off the second and third, and having 2 methyl group, it is actually called dimethyl because di represent 2 of the same thing. So it reads as 2, 3, showing the location of the side chain, and make sure you put di in front of a methyl. There's 2,3 dimethyl butanal. And condensed formula reading from CH3, CH, remember the side chain is in brackets CH3, coming back to carbon 2, CH, another side chain in CH3 in brackets, finishing with CHOs. And have a look at another way to condense it, and you can figure it out by pausing this video, and if you can't get it, just write me a comment so I can explain this to you. And skeletal formula, there's 1, 2, 3, 4 carbons joining together, having an aldehyde, and come back to second and third carbon to represent the methyl group. For this structure, let's elevate one more level by having 2 different functional groups. Oops, I've just noticed that I'm mixing 2 hydrogens here. This one does not deal with 6 carbons because this is a completely different structure from what we were looking at before. We have an aldehyde group, but we do have an alcohol group as well. And when we deal with more than 2 functional groups, it is important to prioritize one over the other. Usually oxygen-containing group takes priority, but since both of them contains oxygen, we prioritize the carbon with double bonds. So aldehyde will take the priority and start counting from the aldehyde end. So we have 5 carbons in a row in the main chain, and this becomes pentanal. But what do we do with the alcohol group? Because we can't use the alcohol as a suffix, we have to bring this as a prefix and make it sound like a side chain. And we're using hydroxy that's coming off from the 4th carbon. So it is called 4-hydroxypentanal. The naming and drawing of the aldehyde is important, but if you take IB or Cambridge, it is also important to know where they're used for. When you go to the museum, there will be a specimen in a jar filled in a liquid, and this liquid happens to be methanal, the simplest aldehyde containing only 1 carbon. And this is perfect because that methanal doesn't allow the growth of bacteria or mold, so it's a perfect stabilizer which is used for the preservation of the specimen. But this is very highly toxic. Not all aldehydes, but some aldehydes will bring distinctive and characteristic smell, just like the one in the cinnamon. This structure that's responsible for the cinnamony smell has 3 different functional groups, starting with a benzene ring. If the benzene is attached to the bigger part of the molecule, you must put ring, or you can call this as a phenyl group. Second group is the C2C double bond carbon, so that's an alkene group. And the last one is the aldehyde, the one that we are focusing today. And when it comes to assessment, make sure you write both carbonyl and aldehydes, because in the exam, sometimes the marking schedule changes from year to year. Then one year examiners are looking for just the carbonyl group. The next year, they might specifically look for the aldehyde in particular. So by writing both of them all the time, you are guaranteed to score the full mark. Coriander is one of the most controversial herbs because of its strong smell. It is widely used in Vietnamese pho, Malaysian or Indonesian curries, or salad, or it could be even hidden in prawn and coriander dumplings. Do you love them? Or you can't stand them because they taste like soap? There are a few different compounds that causes coriander smell, and here's the first one showing a skeletal formula, and you might notice that it's not showing the hydrogen in the aldehyde end. It is okay not to show hydrogen as long as you show the doubly bonded oxygen. So start counting from the aldehyde 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Having 10, the prefix will be dec. And being an aldehyde, there's your anal or anal, it's a decanal. And some of you might wonder, why is December the 12th month when dec is meant to be 10? And this is because in the ancient Roman calendar, there were only 10 months in a year, finishing with December. However, after some time, the seasons never synchronize with the month, so they've added 2 extra months, which is January and February. And because of this, all the months got pushed back by 2, so December being the 10th month got pushed to the 12th, November pushed to 11th, October was actually the 8th month, but now it's the 10th month. So let's have a look at another structure. Having 10 carbons, still the same length of the main chain, but you might notice that there's an alkene group on the second carbon from the aldehyde end. So we need to address the position and the alkene group. So it's dec for 10, 2 is where the C2C double bond starts, En for the alkene, and Al suffix to represent the aldehyde. For those of you who can't stand coriander, it's because they have the gene called OR6A2 gene, which is one of the sensory genes found in chromosome number 11. When the aldehydes bind to this glycoprotein couple receptor, they just have a higher sensitivity to the aldehyde. In other words, the same amount of aldehyde in coriander produces much stronger neural signals, so the sensation is more intense. But why soap out of so many other things? This is because the similar aldehydes are made as byproduct during soap making process. So you are just being reminded of the soapy taste. Now you can tell your mum that it's not your fault that you're a picky eater. It is actually genetic. Since half of your gene came from your mum, she's 50% responsible for it, and it is not your fault at all. I hope you feel confident with aldehydes, so let's move on to ketones. Unlike aldehyde, which is at the end of the chain, ketone will never be at the end of the chain, but it'll be somewhere along the middle of the chain. It doesn't have to be exactly in the middle, but it's somewhere along the middle. And the suffix with ANONE are known, and general formula will be CnH2nO, which you might have noticed it's exactly the same as aldehydes because they are isomers to each other. Now, having the structure of ketone showing a carbonyl group, it must be accompanied by 2 other carbons, one on each side. So this is the critical point for the ketone. This is the only functional group requiring minimum of 3 carbons. So you can't have methanone or ethanone. It is just impossible to have this and the smallest ketone will be the propanone, having 3 carbons. This is known as acetone. You might have heard this from the nail polish remover, and ketone is usually produced from the oxidation of secondary alcohols. Let's get into the business. So still dealing with 6 carbons just like an aldehyde because they're isomers to each other. Remember, it cannot be at the end of the chain, so we have to shift this carbonyl C-double-O bond to somewhere in the middle of the chain. And let's fill up the hydrogen and see if it matches the general formula. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There you are. So the molecular formula is exactly the same, C6H12O, which follows the general formula too. So recognize this ketone group, and we have to start numbering the carbon, and we have 6 carbons in the main chain starting with a prefix hex, and make sure you number from the side that's closer to the ketone. So carbon on the left will become number 1, 2, 3, 4, 5, 6 carbons, and the carbonyl group, the ketone group, is on the second carbon, so it's called hexanone, but make sure you position them so it's hexane 2-one. And the condensed formula, CH3CO, you can even show this as a structure with a C-double-O, but CH2, 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 CH3, and now you guessed it, because CH2 group is repeating 3 times, you could actually use the brackets to represent the repetition of the CH2 groups. And skeletal formula, same drill. We got 1, 2, 3, 4, 5, 6 carbons. Just join them and put your doubly bonded O oxygen. And actually, I'm just rubbing off all the dots just in case if it's an exam scenario. And there's your carbonyl group. And let's actually shift this carbonyl group somewhere along the chain. Did you guess how it's going to be called? I won't bother to draw the hydrogens. It's hexane 3-one. And whenever I think about ketone, I always think about a key. It doesn't actually have the Y, K-E-Y, so it's not a ketone, it's a ketone, but it's good enough to remember that's actually representing a shape like a ketone. So if you shift this carbonyl group once more, then what happens is that counting the main chain has to be starting from the other end because that's a closer end. So it becomes 1, 2, 3, 4, 5, 6 like that. And this is again exactly the same as hexane 3-one, so they are the identical structure. So if you pass the carbonyl group from the middle, there's no point of drawing it because it just becomes reciprocal structure, so you can count from the other side. Let us try more isomers of ketones. So instead of having 6 carbons in the main chain, I'm going to shorten it down to 5 carbons by sliding the carbonyl somewhere in the middle of the chain and have a side chain to make up for 6 carbons. And surely it would have 12 hydrogens as the structure before, and there's your ketone group. And identifying the longest chain as 5, and there's a methyl group highlighted in yellow, and numbering the main chain to show the position of the side chain. So it's a pentane 2-one for the main chain, and there's a methyl group dangling off the 4th carbon, so it's a 4-methyl pentane, pentane 2-one, sorry. So condensed formula, very similar. You can pause it and have a look. But note that I put CH3 in brackets by 2 and see how it works. If you can't work it out, put a comment and I can come back to explain to you. Let's try skeletal formula. So there's 1, 2, 3, 4, 5 carbons, and the methyl group comes off the 4th carbon. I mean, you can do it other way around by going down instead of going up. It's exactly the same structure upside down. And the next structure on the right, which have 4 carbons in a row, having a ketone group, so this makes the longest chain, but I'll be having 2 of the methyl group to make up for the 6 carbons and 12 hydrogens with 1 oxygen. So the main chain will be butane 2-one, counting from the right to left because ketone is closer to the right-hand side of it. And there's a methyl group twice on the 3rd carbon, so it becomes 3,3-dimethyl butane 2-one. It sounds mouthful, but when you apply the systematic naming system, it is pretty okay to understand. And there's your skeletal formula. Pause it and see if you can draw the same structure yourself. If the exam present those complicated structures, don't panic because we can name them all. So these are actually monosaccharides, one's a glucose and one's a fructose, which looks slightly different from what you're used to as a 6-membered hexagonal or 5-membered pentagonal rings. Those are just straight chain structures with 2 different functional groups. Now you can spot it. There's an aldehyde group. And this can be called aldose, combining aldehyde with glucose together. And second structure, notice that I've circled 3 carbons to score the full mark. This shows the ketone, and this is called ketose as well. So let's try to, when you get the question to identify the functional group, make sure you circle it and write both carbonyl and aldehydes for the aldehyde and the carbonyl and ketone to score the full mark. So let's name one structure at a time. So on the structure left, aldehyde will be the starting point. 1, 2, 3, 4, 5, 6 carbons in a main chain. So the main chain is going to be called hexanal. But you might have noticed that there's other functional group, the alcohol group, which will be considered as a side chain by using the hydroxy as a prefix. So there's 1, 2, 3, 4, 5 of those, and this brings pentahydroxy. And finishing with the names to show the location of those side chains coming off from 2, 3, 4, 5, 6 carbon of the main chain. So just gotta do 2, 3, 4, 5, 6 pentahydroxyhexanal. Now you're gonna feel pretty smart if you know how to name this. Let's go to the next one. So ketone being closer to the top of the chain, starting number 1, 2, 3, 4, 5, 6. And ketone, the carbonyl group located on the second carbon, so it is going to be called hexane 2-one for the main chain. And can you identify where the hydroxyl groups are? There's 1, 2, 3, 4, 5 again. On number 1, 2 is a skip because it's going to carbonyl group instead, and the remaining chain, so it's a pentahydroxyhexane 2-one. So if you remember one thing from this video, remember the aldehyde is at the end of the chain, ketone is not. So keep learning, keep practicing, and when you understand the method and apply it, you will get closer to perfect score. So thank you for watching, guys, and see you next time.